Hello, everybody. I'm George. I'm going to present like in-band management agent. So what's an in-band management agent? It's a piece of software that runs on the host and it enables system management. What do we use it for? We use it for monitoring. We use it for telemetry that Panos just presented. It can also be used for things like firmware update. We can use it to like predict failure, we can monitor different components and figure out when they're going to fail. We can also use it for like self-healing. An example would be like memory poison containment, right? You can actually figure out if memory is failing and if a particular address is not working, we can remap it and blow fuses and remap the memory of the DIMM. The question is asked is that why in band? Isn't everything moving to out of band, right? In band still matters. Like there is certain monitoring and management that we can actually do only in band. An example would be like host CPU metrics, and it could also anything with the host, right? Anything host kernel software metrics, and then there are things like memory check exception today that's not actually fully available out of band, and other things like memory poison containment. Right? And another big benefit is the high bandwidth connection. Typically, the server CPU has much higher bandwidth connection to the PCIe. So this matters for things like firmware updates, where the firmware can be large. And if you have basically like a GPU card or an accelerator card and you want to update the firmware, higher bandwidth is preferred. And also that we have much higher processing power of the server CPU. This basically helps us with imagine that you want to do like remote debugging. This is more useful to do in band as well. And it's also that in-band can actually help augment out of band. There are machines without BMCs. There are also machines with limited microcontroller, where basically you use a combination of both in-band and out of band to make things work. And finally, even in like out of band cases, we actually have a host agent that actually runs in-band as well. And finally, there is certain amount of additional cost and complexity of the BMC, especially like the things around like network port usage or how you want to basically tunnel the BMC through. So for those use cases, sometimes you may actually use an in-band agent, and that will actually talk to the BMC and can send the data through the in-band path. So it's not just that it's either in-band or out of band. In-band can actually complement out of band, right? So in the cases where like your server CPU is like fully functioning, you can actually use in-band, and whenever there's a failure, you can actually switch over to out of band. And we should also potentially move agents from both in-band to out of band and vice versa. And finally, that there could be some data that is actually collected out of band, but it's not fully processed. So the in-band agent can actually process this data and augment it. An example is that if you have a limited microcontroller that doesn't have floating point operation, it may just give you like raw bits of data that can be processed in the in-band. And finally, there are also cases where there is actually like an out-of-band path, right? A management plane. An example is that if you have a rack management unit, the whole thing is not actually like in-band, but the agent actually runs on that out-of-band unit. Similarly, you can have a switch, and switches have a control plane, and the management agent can run on the control plane. The control plane itself is out of band, but it's actually running, the agent is running in-band in the control plane. And same way for a smart NIC as well. So this is what the architecture looks like. So you see on the blue, you see the servers, and then the server runs like either a host OS or could be a hypervisor. The key thing is that we run the management in a container. We run the management in like container, and that it exports Redfish telemetry. And on the right, you actually see that there is like a BMC, it's a baseband controller, or it could have a limited microcontroller unit. That's what I call it out as MCU. And so the management container that runs the in-band agent can actually talk to the BMC/MCU, and together they can actually export Redfish telemetry. So the thing is that it's basically like both work together. Same way, instead of a server, you can actually replace it with a rack management unit, and you have the same thing. Or you replace a server with a switch, and instead of the host OS, you basically have a control plane OS. And the same architecture holds true. So what are we trying to do as part of the CSM? We wanted to standardize in-band management agent. We want to enable collaboration across the industry. We want to make it super easy to write conformant agents. And once you write conformant agents, we want to be able to make it easy to share those agents. So we also want to have like common telemetry and common protocol, and that's going to replace the current like N custom protocols that we have today. So we're going to make it super easy to enable collections, storage, sharing, and also analysis of the data. And vendors are going to benefit from the additional data that they can get from users. And hyperscalers are going to benefit from being able to use off-the-shelf components. And we also want to enable like remote debugging and also offline debugging as well. And finally, everybody is going to benefit from the improved products that we're going to get from this additional data. This is going to be the summary/roadmap. Today, hyperscalers have custom implementations and vendors have custom protocols. We want to basically bridge them both. We want to make a simple, extensible standard. This is going to incentivize vendors to adopt it. We also want to support easy incremental adoption. This is going to make it easier for hyperscalers to switch over from the custom implementation to an open standard-based implementation. This is what the timeline looks like. In Q4, we want to basically come up with the Inband-Management-Agent architecture and also list the use cases. And in Q2 of 2022, we're going to come up with the draft specs for the Inband-Management-Agent. With that, I take questions.
Hello? I don't think it's working. Huh?
I can hear you.
Oh, okay. So yeah, so this is good. Thanks for sharing your thoughts. In today's hyperscaler implementation, there are several technologies already used, and some are open source, some are custom.
Yes.
And you talked about the vision about what you're planning to define, but I didn't see the benefits of your proposal compared to what exists today.
Yes.
Could you talk about a little more about what exists today and how that is actually a bottleneck, maybe, and that's why you're proposing a new one?
Yeah, good question. So like to rephrase the question, right? What is the problem with what exists today and how we are going to how the new thing is going to help, right? So today hyperscalers have custom implementation, but the problem with the custom implementation that does not scale, it scales when you have like a very few products and in large volume, right? We get much larger volume if you collaborate across the industry as a whole, right? The problem is that the custom implementation means that it limits the number of things that we can actually support, right? So the cost to add, a new server or a new thing into our data center is much higher if you have this very custom, low-touch implementation that we alone support, right? If you basically make it as part of a standard, others will also benefit from it, and it makes it super easy for us to use off-the-shelf component, right? So most of the problems that we face today is that hyperscalers have the custom implementation that basically does not scale if you have too many products, right? That's one thing we want to solve. Other is that if you ask about the vendors are going to benefit from the data, right? So today they don't not get access to the data, but hyperscalers have access to the data, right? By making it super standardized across both of them, so hyperscalers, and not just hyperscalers, anybody else, right, can actually share the data back to the vendors. And so vendors will benefit from the data and they can actually build better products, right? There are simple use cases about failure modes, like how often does it fail? Like for example, it could be a simple thing like a hard disk motor. You want slightly better performance in the motor, right? Or certain small cases that we can actually solve with data. Today it's much harder to do because they don't have the data. That's what we're proposing to solve. Does that answer your question? Yes.
If somebody else asks a question, please feel free to. So I agree with you what you just mentioned. Let's just take an example, right? For memory errors,
Yes.
EDAC driver, which is open source. It's not custom.
Yes.
Right? And hyperscalers are using quite actively. So how the new approach would benefit a hyperscaler if they already are using EDAC, which is open source?
Okay. So you're talking about, I didn't fully understand the case. It's about a memory driver?
Main memory errors.
Main memory errors? Yeah,
Right.
okay.
Or it could be PCI errors, basically
Okay.
any kind of device errors
Yes.
are propagated through the EDAC driver in the Linux environment.
Yes.
Right? So that's error reporting information available today. EDAC driver is open source, part of the Linux kernel. So there's nothing proprietary there. And it can be scaled across pretty large scale infrastructure.
So that's an interesting use case, right? So if you basically look at it as in isolation, right, what you get is basically the memory error. But what you want is that, like, what's the temperature of the server that's operating it at, right? What else is happening, right? How many DIMMs are actually populated, right? Is there crosstalk across the DIMMs? So all of that data is more interesting, and that may actually result in a very different failure pattern than what you see with just plainly looking at one DIMM, right? For example, it could be like a problem on a particular CPU architecture as well, that if you fully populate all the DIMMs, you have more failures, right? So those are the example of the things that we can actually like do with this data that's not easy to do. Cool.
I think to add to that, right? I think what we want to do is we want to complement whatever is currently available. We want to utilize it and put a wrapper around it to get the full rich set of solution that you want to achieve. Right? Depending on that, right? Some OSs, some models, you may not have it, so you need to put different wrapper there, right?
Yes. That's correct. That's right. Cool.
I'll be quick. Do you also have to define a telemetry data model so the data is consistent between systems, and not just the software interface to collect the data, but the definition of the data?
That's a good question. Yes, there is certain amount of data should be common as well, but we should also allow it to be extensible. It's similar to the question that's asked, right? Different hard disk vendors, some of them may decide to expose a little bit more data. We need to be able to support that as well. Same for every other hardware piece as well. So there has to be a certain number of things that standardize, certain things should be extensible as well.
Sorry, Amit, do you have time for
Yeah,
one more question?
no, continue to ask the question because there is
Yes.
some setup there.
Oh, okay.
Yeah, go ahead,
Okay.
please ask
Yeah.
your question.
So I see the problem, especially thank you for the explanation on that you're trying to tie a bunch of things together more than just a memory error record or something like that. I get that part. But you would need that outer band or in-band, right? Is the in-band versus outer band key, or are you trying to come up with a standardization of a record format that applies regardless of how you access it?
Yes. So we wanted to standardize like both across both in-band and out-of-band. So we don't like in-band matters for certain use cases, and in certain other use cases, out-of-band may just work fine. So we want to basically be seamlessly support both. That's what I also mentioned about complementing. We also want certain things like over course of time, as BMCs get more powerful, we want to move a lot of things out of band as well. So that is not exactly the thing, but the key is like interoperability across both, and then how both can be actually complementary as well.
Sorry, one more thing, just to the other individual that asked the question. So as far as standardizing the data model, right, I think this is one of the objectives of the working group. And as you saw in the presentation from the telemetry aspect that Panos shared with Leandro, there's two things that were focused on. One was the envelope, if you recall that, and you can always go back and look at that. And the other one was the payload, right? So once we get to some standardization, we can always scale. And I think that's the intent of the use model for telemetry.
Yes.
So that applies to what you were talking about in regards to IMA.
Yes, it does. Thank you. Thanks for clarifying.